And we're going to assign, we're going to try to write the correct Lewis structures for this ion. Okay? So, we have one carbon. That will give us 1 times 4 electrons. We have 3 oxygens. We put them in brackets, so it will look like 30. 3 times 6, 18 electrons. We have minus 2 charge. That means we have 2 electrons. So total is going to be 24 electrons. That means 12 pairs. Yes? 12 pairs. The connectivity of atoms is going to be what? Carbon, the least electronegative, and the most electronegative will be around. So here's 1, 2, 3. Doesn't matter how you put them. For Lewis structure, it really doesn't matter. I can put them all like this. We're not talking about the shape. We're talking about Lewis structure. Lewis structure does not give you the molecular geometry, the relative position of atoms in space, just the connectivity, where the lines go. But how they go in space, Lewis doesn't give that to you. So, here's the oxygens, right? And we have how many? 12. We already used 3, so we have how many? 9. Yes? 9. We have 3 oxygens. If you put 3 to each, that makes 9. So here is 1, 2, 3, 1, 2, 3, 1, 2, 3. We're done. Now, each oxygen has 8, but carbon has only 6, right? So we can do this, and then that will make also the carbon to have 8. Yes? So I can do that by writing now this way. Like I said, these lines could be these lines on the terminal atoms. Usually we put them to dots, but make it easier to do that way. Okay? So now the whole thing is 2 minus, right? Remember? So this is the correct Lewis structure. Each one has 8 electrons possibly. We try to do that. If not, then they will have less or more. We know that. We know the exception. Well, this chemical species, you can see, it exhibits the condition, not a phenomenon. It's not a phenomenon. The condition of resonance. So I can write 2 more structures of resonance with double arrow, right? If you probably asking what, write the resonance structure, right? And the only thing we do when we do resonance structures, we move only what? Pi bonds and lone pair of electrons. We do not move sigma, for this class anyway. When you go to organic, you might hear a little bit something different. But we do not move what? Sigma bonds, only pi bonds, pi electrons, and lone pair of electrons. So you can see, if I take this one here and put it there, then I can take this one and put it there. One comes in to this, one comes out. So if I do that, then I will have double here. When you have double, you have 2 electrons. We have single, we have 3 pairs of electrons. Right? 2 minus. And then you can do the same thing. You can put the double bond now here, right? So you can take this one and that one, and you can write another one, have double bond here and single there, right? You don't need to do it. You know how to do that, right? So we have 3 resonance structures. We call them resonance contributors, right, to the electronic structure of carbonate ion. Now, let's find out what is the formal charges of these atoms, right? How do we do the formal charges? So let's take, which one do you want? Doesn't matter. Let's take this one, right? And find out the formal charges of each atom. So let's go for the carbon, the central atom. What's the formal charge of carbon? What do? You can make a circle. There's many ways to do it. The teacher likes this way because he thinks it's better. Okay, it's easier. So what he does is make a circle around the central atom, around the atom that you want to find the formal charge, and he cuts all the lines into half for the formal charge. It's according to the definition anyway. So you cut it into half, half. And encloses also any lone electrons, not participating bonding. We don't have any non-participating bonding, do we? Okay, so what you see now here is what? This line stands for 2 electrons. So here is one, here is the other, right? 2, 1 here, 1 there, 2 here, here, there. That's what they stand for, right? The lines. So how many electrons do you see? bonding electrons and non-bonding electrons, we don't have any. That area in the circle, how many? 4. Then you go to the periodic table and you say when carbon is free in the 4th group, how many electrons has in valence shell? 4. So it seems like it did not gain or it did not lose any electrons. Therefore, the formal charge is 0. You see, you don't have to remember the equation. What you subtract from where and all this. You will never forget it, the way you do it. Okay, so that's what? 0. You do the same thing for the oxygens, right? So for this oxygen, what's the formal charge? You do the circle again. You enclose half of the bonding and all the non-bonding. So you have what? 1, 2, 3, 6, 6, 6, and 1? 7, right? 7. 7. Oxygen is 6th group, has 6 electrons. So it seems now that it gained 1 electron. Electron is minus 1 charge. It seems like, that's why we call it formal charge. It's not a real charge, really, to measure it. Usually, it indicates real distribution, not always. So 7, that means the formal charge is minus 1. And if you do for this oxygen that has a double bond, right, it's going to be what? The formal charge is going to be 1, 2, 3, 4, 5, 6, 6, 6. That means it looks like no gain, no loss. It's going to be 0. If you do the other one here, it's just like this one, so it's going to be, or this one is going to be minus 1. And you can check out if you do them right, because the sum of the formal charges of the chemical species should make the charge of the chemical species. So you have 0, carbon is 0, and then you have 2 oxygens with minus 1, and then the other one is 0, so it makes minus 2. Can you see that? Always. The same thing with oxidation numbers. Usually we don't put the oxidation numbers. Usually, right? Maybe not, we do. How do you do oxidation numbers? It's really a piece of cake. If you have the reader, you have the way to do it. Really good. And that's something that the teacher likes to do it that way. You know, that's his way. Because it's really the same thing. When you go to organic, you will do the formal charges according to this definition. Almost no general chemistry textbook talks about how to do the oxidation numbers. It's really the same thing. It's just one only difference. When you make these circles, you consider which atom is more, which atom belongs to an element that's more electronegative, and you take these bonding electrons, all of them to the side of the most electronegative, and that's it. So, should we do one example? Let's do one example because it's going to be in your exam something like that, because the oxidation numbers. So let's do this one here, so we won't mess up this. Let's do the oxidation numbers there, right? So let's do the oxidation number of carbon, right? Now this is very interesting. If you do for the different resonance structures, the formal charges, you will find out that there will be always atoms in the same position that they will not have the same formal charge. So each resonance structure has different formal charges for different atoms. If you take the different resonance structures of the same chemical species and you do oxidation numbers for each atom, you will see that all of them are identical. Each Lewis structure has the same oxidation numbers for each atom in that structure. It's pretty interesting, huh? So let's do the oxidation numbers now here. Let's go for carbon. So we're going to do a circle now, and when I do the circle, I will always put the lone pair of electrons in the circle, both cases, formal and oxidation numbers. But when I do oxidation numbers, instead of cutting the lines into half, I'm going to go around them, put the electrons into the most electronegative atom. Yes? So I'm looking for oxidation number of carbon. Here's carbon. So, should I go this way? In the middle? No, that's formal charges. Should I go that way or should I go that way? Oxygen is more electronegative than carbon. So this electron is going to go to oxygen. So I'm going to go this way for carbon. Carbon lost them, they don't have it. Carbon and oxygen. This is more electronegative than carbon, so I'm going to go like this. This is more electronegative than carbon, so it's going to go like this. How many do I have in a circle? Nothing. I get the same kind of thinking. How many has when it's free? 4. In this bonding environment, it seems like what? It lost 4 electrons. It seems like. That's why oxidation number is not really charged either. It seems like it lost 4 electrons. So if it lost 4 electrons, it seems like how much charge would you expect? How much charge would you expect? Plus 4. So oxidation number is going to be plus 4. Can you see that? Should we do an oxygen? Okay? So, for this oxygen now, right? I'll make a circle, and I enclose always the lone pair of electrons, either way, formal oxidation numbers. And the electrons will go to the most electronegative. So oxygen is most electronegative than carbon. So this one goes into the circle. There you go. The bonding pair of electrons go to the most electronegative, the oxygen. So they go there. Put them into the circle. How many do I have in the circle? 8. 8. Normally, when it's not bonded to anything, 3. How many has? It appears to have 2 more. Right? It appears to have 2 more. Therefore, the oxidation number is? No, wait a minute. We have 6. We have 8. Yeah. We have 1, 2, 3, 4. 8. Okay, so it appears to have 2 more. So it's going to be oxidation number what? -2. -2. If you do this, you will find the same thing because it's the same chemical environment. Can you see it? Single bond, right? So this one is going to have also what? This one is going to have also -2. And if you do also this one, 1, 2, 3, 4, 8, they all have 8, right? So that one will have also what? -2. Yes? Each one has -2. Remember, the same rule. The sum of the oxidation numbers is equal to the charge of the species. Is it? Let's see. -2, -2, -2, that's 3 times -2, plus 4, how much it makes? Pretty cool, huh? Can you see it? Very easy. If you understand this way, you can do any chemical species from the Lewis structure, and you will never forget it. If you remember how we thought. You don't need to remember equations and what you subtract from where. In fact, by doing it this way, it makes sense. Because you compare what's the charge compared to when it's free in this bonding environment. Right? Okay? Now let's do some problem maybe with numbers and grams and stoichiometry. Huh? It's time to do that, huh? What do you think? Should we?